Okay, hi everybody. So this is a day over this is a section over section 6.1, video over section 6.1. Don't forget that you will need a guided notes for this, so please get that from the sub if you have not already. Again, please fill out all the guided notes. I'm going to be checking that when I get back. Guided notes. I want all guided notes completed. Okay, that's really important. I will also be checking the homework for this section as well. Okay, so let's get to it. Now, what is chapter 6? We just finished out chapter 5, which is all about straight line functions. So now, chapter 6 is all about how do we take, what is the solution when we put two straight line functions on the same graph? That's really what we're talking about in this entire chapter. You know, what happens when two lines cross? Or what happens when we put two lines on the same graph? That is called a system of linear equations. Okay, a system of linear equations is just a set of two or more linear equations containing two or more variables. Okay, so you know, this word system could be replaced with set. Okay, it's a set of linear equations. It's two or more linear equations. We could have 3, we could have 4, we could have 5. Okay, we could definitely put more than one linear equation on the same graph. Excuse me. So what is the solution? You know, what is the solution to a system of linear equations? Well, the solution is the ordered pair. Please go ahead and underline that. The ordered pair that satisfies each equation in the system. So if an ordered pair is a solution, it will make both equations true. Underline that one as well, okay? So it's got to work for both equations, not just one of them, but both. This is basically how you check an answer, okay? So this is an example of a system of equations, this right here. Okay, we've got this brace-looking thing, and then we've got an equation on the top and then an equation on the bottom. Okay, so how do we work with it? Well, to check an answer, say I somehow, you know, some way, and this is what we're going to learn in this chapter, somehow solved for the system of equations. And we got this coordinate 5, 2. Now, if you wanted to check your answer, what you could do is you could plug in that answer to both of those equations, okay? We could plug it into both of those equations. Okay, now here's what this means. I have 2/5 times, well, what's my x value? 5 minus 2. Is that indeed equal to 0? Because if it is, then I know that it meets this first equation. Okay, well, what's 2/5 of 5? It's 2. 2 minus 2 is 0. Does that come out to be a true statement? Yes, it does. So I know 5, 2 is a solution to that first equation. But is it a solution to the second equation? Let's check. 3 times 5 minus 2. Is that indeed 13? 15 minus 2. Is that indeed 13? That checks out. So is 5, 2 the solution? Yes, it is. Okay. All right. Okay. Now, you know, I'm just going to jump back to see if this is still working. Yep, it is. Okay, good. All right. So let's take a look at the second one here. Okay, is this a solution to the system? Is this a solution to the system? Well, why don't you guys pause and try it? See if it is a solution. When you're ready, go ahead and play. All right. So we got -2 plus 3 times 2, because again, x was 2, x was -2, y was 2, is equal to 4. Is that a true statement? -2 plus 6, is that indeed 4? Yeah, so that checks out. Now let's check the other one. -2 plus 2, is that 2? Ooh, is this a true statement? No, it is not a true statement. So while it works for the first equation, it does not work for the second equation. So we say that it is not a solution to the system. Okay? So basically what that's telling us now is that I don't know how I arrived at -2, 2, but it's not right. You got to go back and check your answer, or you got to go back and check your work. All right. So let's talk about, from this point on, we're going to talk about How do we solve these things? How do we get those coordinates? Okay. All right. All solutions of a linear equation are on its graph. Okay. To find a solution of a system of linear equations, you need a point that each line has in common. In other words, there you need to find their intersection. Go ahead and box that in. What does that mean? Take a look at these two lines. If I wanted the solution to the system of the blue line and the red line, it would occur at 2, 3. It's where the two lines will cross. Visually, it's where the two lines will cross. Don't believe me? Let's check that answer just like we did on the last slide. 3 is equal to 2 times 2 minus 1. Does that come out to be a true statement? Yeah. Does the second one come out to be true? 3 is equal to negative 2 plus 5. Is that a true statement? 3 does equal 3. Look at that. So graphically, the solution to any system is where the two lines are going to cross. Now, it's nice with this one because it's crossing at a nice clean point. Okay? We can see that on the graph pretty easily. 2, 3. Okay, and that's just graph. Look, the blue line, 2x minus 1. Y-intercept of negative 1, rise 2, run 1, rise 2, run 1, right at that point. Negative x plus 5, y-intercept of 5, down 1, right 1, down 1, right 1. Look, it crosses nice clean point right there. Okay? So let's practice that. Now, I want you all to graph these, okay? I want to see every graph on there. Okay. So let's take my first line. Now, I'm going to color code these. Feel free to do that the same. Okay. Now, for my blue line, the slope is negative 2, and the y-intercept is negative 1. Look how nice. It's already in slope-intercept form, so that's really easy to graph. Y-intercept of negative 1, slope of negative 2. Down 2, right 1, down 2, right 1, down 2, right 1. Sound like a robot? I'm not a robot, though. But if I was a robot, would I really say I'm not a robot? All right, take a look at the red line. Y-intercept of 5 and a slope of 1. Y-intercept of 5 and a slope of 1. Up 1 over 1, up 1 over 1. Look, I'm going away from my graph. Don't I want to go down toward my graph? Bink. Bink. Look at that. Crosses it. Nice clean point right there. Where is that location? Where is that coordinate? Negative 2, 3. That's the answer. Excuse me. That is the solution. Don't believe me? You could obviously check your answer by plugging it back in if you really needed to. But trust me, it is. Okay. Get out of here. Get. Okay. Oh, that's all that's on that page. Why don't you guys try this one? Now, the only issue here is that the red line is not solved for y. You can't really easily tell what the slope is and what the y-intercept is. So go ahead and solve it for y as well. I'll give you a minute. All right. Okay. Let's take a look at the blue line. Slope is 1/3, where the y-intercept is negative 3. Okay. Up 1 over 3, up 1 over 3. See, with the first line, you're going to have to make a lot of dots. Down 1, left 3, because you don't know where the other line is going to end up quite yet. So make dots all through. Make dots all throughout the graph. Now for my red line, we subtract the 2x over to the other side. We get y is equal to negative 2x, and then a plus 4. Y-intercept of 4, and now go toward your other line. Down 2, right 1, down 2, right 1, down 2, right. Bingo. Here it is. 3, negative 2. Why are they all 3s and 2s? There's my answer there. Okay. All right, we got a word problem here. Ren and Jenny reading the same book. Ren is on page 14 and he reads 2 pages every night. Jenny is on page 6, but reads 3 pages each night. After how many nights will they have read the same number of pages? And how many pages will that be? Okay, let's make an equation for each one. Ren, y equals 14 plus 2x. Jenny, y equals 6 plus 3x. Okay, so my slope is 2. My y-intercept is 14. My slope is 3. My y-intercept is 6. Okay. So what is x? X is the amount of pages read every night. I'm sorry, the amount of nights. Okay. What's the y-axis? The total number of pages, right? All right, now, if I start at 14, I want to try to scale this, right? So let's go every 2. 2, 4, 6, 8, 10, 12, 14. Okay, so this is Ren, 14. Now, I have to be careful here, okay? Because my slope is 2, so I'm not going to go up 2 over 1. I'm going to go up 2 over 1 box, right? Because isn't this going by 2, right? Didn't we just count this by 2s? So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and so on. Because I'm only going by 1 day at a time over here. All right, now, my Jenny, 2, 4, 6. But I'm going 3, up 3 units over 1 unit, up 3 units. Oh, sorry, didn't make a point there. Up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1. Oh, geez, I should have plotted it better. Up 3 over 1. Oh, I think I got it right on there. Okay, good. Okay, so where's that point going to occur? Now, you have to plan accordingly. Oops, should have been green there. You have to kind of, not plan accordingly, but go through. How many nights? 1, 2, 3, 4, 5, 6, 7, 8. 8 nights. What's the pages? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21. Oh, shoot, I lost count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30 pages. Okay, 30 pages. And how many nights? What did we say? 1, 2, 3, 4, 5, 6, 7, 8 nights. All right, there it is, folks. Now, a little bit later on, we will talk about an easier way to solve this problem other than graphing. And you're going to be like, oh, man, that's nice. Okay, but for right now, all we know is graphing. Okay, don't forget to do your homework, people. Let me tell you what that is. The homework is on page 386. 9 to 16. Make sure you use graph paper, okay, when it asks you for it. All right.